Okay, welcome to the NUPOC Video Study Guide number 62. This is another related rate problem, and I know we've been going gangbusters on these related rate problems for the last few videos. But I promise the next one will be an optimization video. I've already got the problem picked out, but we're gonna go through another one of these because they're really important and they're just really great. Very applicable questions that get asked a lot. And this question in particular I like because it's not just a straight up related rate problem. There's a little bit of a twist to it, and you got to think about it a little bit more. You got to plan out how you're going to do it, and so if you're not paying attention, you can kind of get stuck. And it might be a problem maybe that would be more something that would be asked of, say, an NR engineer candidate instead of like a subs or surface guy going in there, just because they just want to see how you think when you come up against something where you hadn't planned for it or something. But anyways, so let's get into it. So this problem says that we have a spherical raindrop, and then it falls through some dry air and evaporates at a rate proportional to its surface area. And it wants us to show that the radius of this raindrop decreases at a constant rate, okay? And this makes sense. I mean, that's kind of intuitive, right? That if you have a large surface area to your raindrop, right, it's going to evaporate more rapidly. And if it has a small surface area, there's less surface area exposed to the air, it's going to evaporate less rapidly. There'll be less air molecules knocking off water molecules. There's less surface area for electrostatic forces, all kinds of stuff that can cause this raindrop to kind of evaporate and come apart. But anyways, so let's start by drawing it out, because it's always good to do that. So we have this sphere here, and this is our raindrop. Let's see if I can draw that reasonably well. Okay, and it has some R, and of course it has some surface area. I'll call that S, and inside it has some volume, right? Okay. So we know that it evaporates at a rate proportional to its surface area, and evaporation implies a change in volume, right? So that's dV dt. Okay, that's evaporation, and it's proportional to the surface area S. And since we're evaporating, that means that the volume is decreasing, so dV dt is a negative number. So I will say that it's proportional to S by this constant K, and it's also negative. dV dt is negative. Okay, we could get rid of the negative sign and just say K is a negative number, but let's be very deliberate about our negative signs and all these things so that we don't lose track of them. Okay, so we have dV dt is equal to minus Ks, okay, where K is a constant and S is the surface area. And we know the surface area is 4 pi r squared, okay? So that's great, but that's not really, a related rate problem, right? Because we have dV dt, but we don't have dr dt. We have just this thing in terms of r, and we don't want to take another derivative because then we'll have the second derivative over here. So kind of where do we go from here? What's the strategy for solving this? How do we show that this radius is changing at a constant rate? Where do we get our dr dt from? We're not going to get it from here. So the way to do it is to step back and say, okay, well, what else do I know? Well, it's still a sphere, so even though the volume is changing at any particular time, the volume, the instantaneous volume, will still be 4/3 pi r cubed, right? R is changing, but at any particular r, that's still true. So let's go ahead and apply our related rate strategy to this. So let's take ddt of each side, right? So on the left, I will get dV dt, same as what I have up here, right? And on the right, of course, 4/3 pi is a constant, that comes out. And of course, we'll get dr cubed dt, which we've been doing this for a while now, right? We know how to do the chain rule, the implicit differentiation, right? So this will become dr cubed dr dt, and so now we've found our dr dt, right? And so we'll have dv dt equals 4/3 pi times 3r squared from this dr cubed dr and dr dt. Okay, and of course this 3 will cancel with this 1/3, and we'll get 4 pi r squared dr dt. Okay, so we have dv dt equals something up here, and dv dt equals something else down here, right? So they both equal dv dt, so let's just go ahead and equate them, right? So we will have minus k 4 pi r squared up here, right? That's what dv dt was equal to up there. And that equals right here, 4 pi r squared, 4 pi r squared dr dt, right? So it's pretty obvious at this point. Let's just divide both sides by 4 pi r squared, okay? And we have dr dt equals minus k. So there it is. So the change in the radius is equal to a negative constant number, which means the radius itself is changing at a constant rate and it's decreasing, right? So the radius, right, if we were to graph it over time, right, and this is r, it's just doing something like this, right? And I don't know if this is off the screen. Let me check real quick. Nope, just barely on the screen, right? And if this is dr dt, well, maybe it'll be a little bit off the screen. I'll try to draw it right here. It's a constant negative number, right? So there you go. Move that up a bit. So that's it. That's the strategy to show that for a raindrop that's evaporating at a rate proportional to its surface area, that's how you would show that the radius is decreasing at a constant rate. If you want to go through this on your own with another reference, and maybe they've got a solution that makes more sense to you, you can find this problem at that link that I provided several videos ago now. But the link should be in the description. The link to that video should be in the description on this video. But anyways, this should be at that calculus text, that online calculus text in their problem sets, and it should be under section, I believe it's 2.6, problem 39. So it's an odd number problem, so there should be a solution there for it. And you know, maybe their solution makes a little bit more sense. Maybe they skipped steps that we did, and maybe I skipped some steps that they did. But anyways, if you want to use that reference, there it is.